Okay, let's get this started. I'm going to ask you a very simple question. You are in AP Calculus BC now, so you should be able to answer this question. And the question is, what is the square root of 9? Think about it. Do your calculations. No calculators. And let's see what your answer is. Well, some of you may say the answer is just 3. Some of you may say the answer is -3 or +3. And some of you might get creative and use an imaginary number I in there. So what is the square root of 9? Come on, BC Calculus. This is not a good start if you don't know if it's this one or this one. Okay, the answer to this question, what is the square root of 9, is just 3. But wait, you might say, -3 squared is 9. That's true. You may say that 3 squared is 9. Also true. So you may want to argue, wait a minute, the square root of 9 is plus or minus 3. It's not. It's only 3. You see, the square root is a function operator, and the function operator can only produce one output for any given one input. So if this produced plus or minus 3, well, then it wouldn't be a function. It can only produce 3. So why is it +3 and not -3? Well, a long time ago, mathematicians got around, they rolled the dice, they flipped a coin, and then they decided, you know what, let's stick with the +3. It's a little more simple, and that'll be the standard. And they called it the principal square root. It's a decision that was made to produce the positive root always. And you knew this. You know that the square root of 25 is 5. Now, there does arise occasions when you're solving equations and you get plus or minus, and I'm going to address that here. But before that time, let's define the square root of x squared. So what is it? If you say x, you are wrong, because that allows for negative numbers. We want only the positive root, and to ensure that it's positive, we say it's the absolute value of x. So the square root of x squared is the absolute value of x. Now, what is the absolute value of x equal to? Well, it depends what course you're in. Some will say it's the distance from 0 on the number line, and they're not wrong. But I want to write this as a piecewise function. Sort of, if I'm programming, I want to say if I plug in let's say 3, it's going to return 3. If I plug in -5, it should return a +5. So that programming says if the number is positive, it's going to return itself. And again, that's with the provision that x is greater than or equal to 0. It's going to be the opposite of the number, provided that the number we input is less than 0. So, for instance, again, if I say what is the absolute value of -5, well, that number is less than 0, so I'm going to return the opposite of -5 to return +5. This one here, let's say the absolute value of x plus 1. This one's not in your notes packet, but I'd like to just address it. So if I use this definition of the absolute value using a piecewise expression, well, the x plus 1 is going to return the interior x plus 1. That's provided that the interior is positive or possibly 0. And it's going to be the opposite of the interior, provided that the interior is less than 0. And if I simplify that, then I get x plus 1 will be the expression, provided that x is greater than or equal to, subtract 1 from both sides, so greater than or equal to -1, and it's going to be -x minus 1, provided that x is less than -1. So real briefly, I just want to go over the problem that says x squared is equal to 9, and why the answer is plus or minus 3 if you were showing your work. Well, the first thing you would do is take the square root of both sides. And here's where we're going to be a little more advanced. Before, you would just say x is plus or minus 3. But actually what's happening is that the left-hand side is returning the absolute value of x, and the positive side, or the right side, is producing the principal square root of +3. And there we go. And now we're saying that the interior x can equal 3. or the interior can equal -3. We are next going to discuss continuity. Look at these three graphs and listen to the question I'm going to pose very carefully. I'm asking, is the function continuous at, hear the keyword at, is the function continuous at x equals a? For the first one, is the function continuous at x equals a? No. This open circle means we have a hole there. For the second one, is this function continuous at x equals a? No. You see, we have this, what's called a jump discontinuity. And in the third one, the function is also not continuous at x equals a. This one is called removable because the function is defined at x equals a, but there is still this hole, and this point has been removed, so to speak. Now let's pose a different question. The question I'm asking now is, does the function have a limit as x approaches a? And in the first one, it does have a limit. The function is getting closer and closer and closer to L, even though it's not continuous. In the second one, well, this one does not have a limit because as we approach from the right and we approach from the left, we get different values. The third one, this one also has a limit. And the limit, let's say, is L. Even though this point doesn't follow that limit, as we get closer and closer and closer to a with x, the function gets closer and closer and closer to L. So the first one and the third one have a limit. So limit and continuity are not the same thing, but often get confused. So let's do a definition for a function continuous, again this keyword at x equals a. In order for a function to be continuous at x equals a, the limit as x approaches a of f of x, well, it certainly has to exist. It has to have a limit. And that limit has to equal the value of the function at a. In this third example, f of a existed, so that's good. The limit existed, but then they were not equal to each other, so the function was not continuous at x equals a. A theorem here is talking about the limit and the limit only. You don't always have to use this theorem, but it is wise to use it when you have a piecewise function where the behavior is different on either side of a. So here, the limit as x approaches a of f of x is equal to L if and only if, so I used a double F. I actually needed that here too. If and only if. Okay, back to the statement here. The limit as x approaches a of f of x equals L if and only if the limit as x approaches a from the right-hand side of f of x equals L, and also the limit as x approaches a from the left-hand side of f of x equals L. Now this theorem is about the limit portion. It is not sufficient to find that it has a limit and conclude that it's continuous. That's not sufficient. It does, though, prove the existence of the limit portion of the continuity definition. We would also need to show that it's equal to the value of the function at x equals a. Now we're going to do a formal proof. We're going to prove that f is or is not continuous at x equals a. I would like you to follow this format of the proof so that you don't skip any important elements of it. The first thing we're going to do is show that the function f has a value at the question point, in this case a equals 1. So f of 1 is equal to, well, I would plug that into the top. I don't necessarily have to show this substitution, but I could, and that equals 3. Okay, f of 1 equals 3. It exists, and it equals 3. In step 2, we're going to find the limit. This is only a limit portion of the proof. Now, I noticed because of my piecewise function, the behavior to the right of 1 is different than the behavior to the left of 1. So to find the limit, I'm going to have to take two separate statements, that theorem that we talked about. I'm going to take the limit as x approaches 1 from the right-hand side of f of x. I want you to follow this format carefully. I want you to use the f of x generically first. Then after that, you're going to say the limit as x approaches 1 from the right, and then we pluck the behavior of the function to the right, which is 5 minus 2x. Now, to find that limit, we simply substitute it in, and we get 3. Okay, I'm still in step 2, but I'm trying to find the limit, provided that it exists. Now we're going to find the limit as x approaches 1 from the left of our function, and I have to write the generic f of x, and that's the limit as x approaches 1 from the left, and then I put the behavior to the left, which is x squared plus 1. Substituting that in, we get 2. And since those are different, this function will not have a limit. So I'm going to come down here, I'm going to write this therefore statement. Notice the therefore statement is in line with the limits, so that's local to step 2. We're going to say that the limit as x approaches 1 period of f of x does not exist. That leads us to step 3. In step 3, I want a clear indication of the definition for continuous at x equals a. So here, we're going to say the limit as x approaches 1 of f of x is going to be compared to f of 1. And they are not equal. And now my therefore statement, following underneath the I, double I, triple I, is going to say, therefore, f is not continuous at x equals 1. Now, using some logic, you could have done step 2 first, found that it doesn't have a limit, and then it would not matter what f of 1 is. You could still then skip to step 3 and say that they're not equal. The minute one of these things, either step 1 or step 2, fail to exist, then you automatically can't have them equaling each other. Now, if we support this graphically and show the piecewise function, we have a linear equation, and that's to the right of 1 and including 1. And then we have this quadratic equation, and that's okay. You can have linear and quadratic. If that was maybe shimmied up a unit, then this would be continuous at x equals 1. But here we have a jump discontinuity. F is not continuous at x equals 1. In example number 2, we are trying to formally prove whether g is or is not continuous at x equals 2. Before I do the formal proof, however, I'm going to rewrite g. Okay, I'm going to rewrite it using that definition of absolute value. So this can be x minus 2 over x minus 2. Remember, it returns itself, this self being the numerator, and that's provided that x is greater than 2. I'm tempted to put an equal sign here, but it can't equal 2 because then the denominator would be 0 and we can't divide by 0. Anyway, it's going to be the opposite of the numerator, provided that the numerator is less than 2. And then this portion here of the piecewise equation tells me that the function is going to be 0 when x equals 2. I'll simplify this up, and I get 1. The function g is just 1, provided that x is greater than 2. The function g is negative 1, provided that x is less than 2. And the function g is 0, provided that x equals 2. Let's do our formal proof. Step little I, g at 2 is equal to 0 because it's defined as such. Step 2. We're going to do the limit or find the limit, but this is also piecewise. The behavior is different to the right and left of 2, so I need 2 separate limit statements. The limit as x approaches 2 from the right of g of x is equal to the limit as x approaches 2 from the right. So remember, I always have the generic function, in this case g, and then I model the behavior. The behavior is just the number 1. So g is 1, and then the limit of a constant is just a constant. Do not skip any one of these 3 portions, please. Next, the limit as x approaches 2 from the left of generic g of x, that's going to equal the limit as x approaches 2 from the left. The behavior to the left is negative 1, and so the limit's negative 1. Okay, So I locally want to conclude, therefore, the limit as x approaches 2 of g of x period does not exist. Step 3, the limit as x approaches 2 of g of x does not equal g at 2, and therefore g is not continuous at x equals 2. And now our graphical support. Please notice that I did highlight a point here because when x was 2, the function was 0. I also want to point out that these are not supposed to be hard. You should be able to look at it without doing any work and decide the answer. So my focus is not going to be, do you know the answer? You better know the answer. My focus is going to be, can you communicate the answer formally in the form of a proof? Okay, example number 3, we're going to try to prove whether P is or is not continuous at x equals -1. Let's do this now. Step 1, P at -1 by definition is equal to 4. Step 2. Step 2 is all about the limit. I want to point out here that the behavior to the left of -1 and the behavior to the right of -1 is actually the same. The only time the behavior stops is at the instantaneous point when x is equal to -1. So I do not need 2 limit statements here. I need but 1 limit statement. I'm trying to find the limit as x approaches -1 of p of x, which equals the limit as x approaches -1 of the behavior of p, and not including -1, but the behavior of p otherwise, which is just x squared minus 1 over x plus 1. Now you should know from a previous course to find this limit, all we have to do is factor the top, x plus 1, x minus 1 is the factorization of the numerator, x plus 1, and then I'm going to cancel this out. Please be careful when you cancel out, that's not sufficient. We want to write the result after simplification, and so x approaches -1 of x minus 1. Now we are in the position to substitute, and so the limit is -2. So here the function existed at -1. The function also has a limit at -1, but those are not equal. And therefore the limit as x approaches -1 of p of x is not equal to p at -1. And therefore p is not continuous at x equals -1. I want to answer a question that you might have. Notice that there is no therefore statement here. I don't need a therefore statement because it reads left to right. It reads, what is the limit as x approaches -1 of p? What is it? 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 It's -2. I don't have to say therefore it's -2. I've already shown that it's -2. And the graph of this shows that we have a line with a removed point. We have a removable discontinuity.